Welcome to AI with Avinash Sir. What if I told you atoms hold secrets beyond classical physics? Dive into quantum theory, where the invisible rules of our universe reveal themselves. Welcome. This video explains quantum theory in chemistry. We will explore Schrödinger's equation to eigenvalues, step by step. Quantum theory transforms our understanding of microscopic particles. It provides a framework for predicting behaviors that classical physics cannot explain. Today, we'll start with the Schrödinger wave equation. In 1926, Erwin Schrödinger introduced a mathematical approach. This equation describes how microscopic particles behave. It's based on the wave nature of particles. Let's break it down. First, the time-dependent Schrödinger equation looks like this. I, h bar, frac, partial, psi, partial t, equals, hat, h, psi. Here, I is the imaginary unit. H bar represents reduced Planck's constant. Psi is the wave function, which captures the quantum state. The Hamiltonian operator, hat, h, relates to total energy. This time-dependent equation shows how the wave function changes with time. Now, we have the time-independent Schrödinger equation. It simplifies when potential energy remains constant. It takes the form, hat, h, psi equals e, psi. This equation is crucial in chemistry, especially for hydrogen atoms and particle-in-a-box problems. Now, let's dive into operators in quantum mechanics. These are mathematical expressions for measurable quantities. The position operator is straightforward. It involves multiplication by position. The momentum operator is a bit more complex. Hat, p underscore x, equals I, h bar, frac, partial x. The Hamiltonian operator combines kinetic and potential energy. Next, we'll discuss the wave function, represented by psi. This function denotes the quantum state of a particle. The square modulus, psi, squared, signifies the probability of locating the particle within a specific range. Born's interpretation emphasizes this idea. It tells us how likely we are to find a particle between 2 points. Let's talk about normalization and orthogonality. Normalization means the wave function's total probability equals 1. Mathematically, it looks like this. Int underscore, infty, caret, infty. Psi, x, squared dx equals 1. Orthogonality asserts that different quantum states are independent, shown as int psi underscore m caret asterisk psi underscore n dx equals 0 for m does not equal n. The concepts of eigenvalues and eigenfunctions are next. The operator equation is hat a psi equals a psi. In this equation, hat a denotes the operator, a indicates the measured value or eigenvalue, and psi is the allowed state or eigenfunction. Specifically, applying the Hamiltonian gives us hat h psi equals e psi. The Schrödinger equation is paramount in chemistry. It helps us understand electron orbitals' shapes and energy levels. We analyze transitions in spectroscopy using these principles. Quantum numbers along with atomic and molecular structures are grounded in this theory. To sum up, quantum theory provides a precise mathematical framework for chemistry. We've explored the Schrödinger equation, operators, wave functions, normalization, orthogonality, and eigenvalues. Join me, AI with Avinash Sir, in our next session, where we'll explore the microscopic world further.